Statistics. Today we'll be talking about the mean, the standard deviation, and large counts condition. This is day 3. Is it a fair coin? Okay, go ahead and open up to your packets. So this is what we did, is that I gave everybody a coin and I asked them to toss it 30 times. Then I asked them to go ahead and record how many times they got heads. I asked them to do it again and again and again. So we did it 4 times. And this is the results that I got. So if X is the number of heads, then we see that for a binomial random variable, remember the formula for a binomial random variable, because I have SPIT, I have success failure, probability the same, they're independent, and the trial is a set number because we had 30 times, that the formula for the mean is going to be NP. And so that means the mean amount of heads I should expect to get is 30 times 0.5, which is 15. And the standard deviation, remember my formula, is square root of NP1 minus P. And I get 30 times 0.5 times 0.5, which is 2.74. Okay, so for the sample proportions, what I need to do is instead of me having means, I want a sample proportion, I will then divide my proportion by 30, because 16 divided by 30 is 0.53. That's where that comes from. 13 divided by 30 is 0.43, 17 divided by 30 is 0.57, and 15 divided by 30 is 0.5. So if I'm asking what is the proportion of heads, that's how I'm getting it. Not just the number of heads, I'm asking the proportion of heads. Similarly, if I do the same thing to my mean, if I say, okay, instead of the average number of heads I will get, I'm asking for the proportion number of heads I get. So I'm just going to divide that by 30. And I get 50%. I'm going to do the same thing for my standard deviation, and I get my standard deviation that I got above with the 2.74 and divide it by 30, and I get 0.091. So if I record each value on a different sticker, what we didn't do the sticker and the dot plot, we did the calculator and we sent it to I sent it to you and you sent it back, and we went ahead and put it together, and we saw that the sampling distribution is going to be approximately normal. The condition that allows it to be approximately normal is that I have successes and failures. NP is the success. So I have 30 flips times P, 50%, and that's how many heads I got, and that's greater than 10. Then N1 minus P, 30 times 1 minus P, 50% is greater than 10, and that's tails. And that gives me the large counts condition and says, okay, it's approximately normal. So if I were to draw a normal distribution, I would have my mean as 0.5 and my standard deviation of 0.091, which I got from number 4. And you can see I found the z-score and found it from the table. But remember, I can do normal CDF also on my calculator. To get normal CDF, remember it's menu, stat, distribution, and normal CDF. So that's 653. And the lower bound would be 0.7. The upper bound, it goes forever and ever. I'd put anything that's way off the chart, so I'm just going to put like a bunch of 9s. The mean is here at 0.5, and the standard deviation is 0.091. And I would get the same thing that I would get here that's demonstrated on the chart. If I toss a special quarter 30 times and get 21 heads, does that provide convincing evidence that the quarter is unfairly weighted? Well, 21 heads is 21 out of 30, and 21 out of 30 is that 70%, which is 0.0139, and since that's less than 5%, we consider that very unusual, and we consider that unlikely to happen. So for the sampling distribution, the formulas that are on your formula chart is, first of all, the mean of p hat, this is on the back side of your formula chart on the top row, is equal to p, and the standard deviation of the sampling distribution is square root of pq over n. The large counts conditions, which is my successes and my failures, as long as both of those groups are greater than 10, my shape is going to be approximately normal. And you see the normal, when I'm doing the normal model, remember it's normal CDF, and of course I get that from menu 653. My lower bound is going to be the leftmost shaded area, which if the lower bound's on the left side off the chart, then we just put like negative 9999. The upper bound is right here where it stops shaded, and the mean and the standard deviation are given to you here as the mean and the standard deviation. Okay, so for what spot on my potato chip, of course, go ahead and make sure you do these, and the explanation is as follows. Calculating the mean and standard deviation of the sampling distribution, well, the mean is right here, is given to me at 0.08, and the standard deviation is going to be 0.08, 1 minus 0.08, and then divided by n. So the next one, justify the sampling distributions, approximately normal. Normality, remember, is going to be NP and N1 minus P. And as long as both of those samples or both of those results are greater than or equal to 10, then we can say that sampling distribution is approximately normal. If we use the probability, we can go ahead and do it like this, finding the z-score in the table, or we can go normal CDF. The lower bound is going to be 0.11. The upper bound is going to be 9999, super high. And the mean, of course, is 0.08. And the standard deviation is what we found it was up here, which is 0.012. And if you go ahead and put that in, you will see that what comes out is the same as what we got on here, which is 0.0062. So if we have a simple random sample of 500 potatoes and we find that 11% of the potatoes are blemished, based on this answer, is this going to be evidence that all of the potatoes are blemished or greater than 8%? Well, because it's very unlikely to get 11% or greater, because we found that it's 0.0062 or 0.62%, it's a 0.62% likelihood that I find that 11% or more are blemished. So there's convincing evidence that the proportion of all potatoes are blemished is greater than 8%, because I found that that is unlikely that this is occurring by chance. Okay, I hope that helps you, and we'll see you later.